What I thought I'd try to do in the course of half an hour is cover several things. First, I'm going to talk a little bit about how one studies cognitive evolution, a little bit more about cognitive archaeology in particular, then talk about what I mean by a mosaic pattern in evolution, and then give you one particular example. We don't have time to do them all, but I'll pick one that I rather like. There are four basic methods that are used in evolutionary science. There's the study of fossils. There's the comparative method, studying non-humans. There's the study of development, or ontogeny. And then there's reverse engineering. For human evolution, at least the last 2.5 million years of human evolution, there's also archaeology, which is what I do. And my particular interest in archaeology is trying to reconstruct things about human cognitive evolution. And I thought I would, for a few minutes, talk a little bit about how one studies cognitive evolution, because we use all of the methodologies I mentioned before. Probably the most obvious one is to look at the evolution of the brain. And this is the field of paleoneurology. Of course, brains very rarely fossilize, but skulls fossilize. And the internal table of the skull actually preserves a little bit of the external shape of the brain. And from that, we can learn some things about the evolution of the brain. This is a particular example. On the left, you have what we call an endocast of the brain of KNM 1470, which is an early Homo. And on the right, we have an endocast of a modern human cranium. And this, of course, tells you a lot, right? So you can look at this and the information just jumps out at you. Turns out that the thing we can study most easily is size. Doesn't sound very exciting. We can do some things in terms of cerebral asymmetry, that is the general asymmetry of the lobes of the brain. And some in paleoneurology think they can do a bit more than that. For example, some think they can identify a structure called Broca's area, or Broca's cap, which is right here. And if you look on this one, you see it has one too. Exciting, yes? Of course, the problem is interpreting that. It turns out that chimpanzees have a Broca's area. They don't use it for speech. So the fact that this one has an expanded Broca's area, does that mean they were talking? What do you think? Not necessarily, as it turns out. So it's not all that easy. It's really hard to interpret these things. The second major approach we use in cognitive evolution is comparative evidence. We do this a lot, and this is primarily looking at non-human primates. And much of the way we think, much of our cognition is the way it is because we're primates. That is, it's something we share with chimpanzees, with monkeys, going all the way back. So if you want to study cognitive evolution, one of the things you have to do is understand the cognition of non-human primates. And there are two basic camps in primatology. If you've studied this at all, you know this. There are the ethologists who study primates in the wild, and there are the experimentalists who study captive primates. And not surprisingly, they can't stand one another. I have another interesting anecdotes about that, but for various reasons. But you can get two basic things from comparative evidence. The first is an understanding of the things we share. The second is identifying the things we don't share. So without the primate evidence, we might think that we were pretty special. But it turns out the list of things that we actually do that primates don't do turns out to be relatively small. A third avenue of approach is by studying development, in particular child development. This is a classic example of Piaget's conservation task. If you've had any developmental psychology, you've been exposed to that. And in this case, a child has two beakers with equal amounts. And they take one beaker and pour it into a taller beaker, then ask the child which one has more, and the child is perfectly confident that this has more. It's called the conservation task. Now, so what? Well, what ontogeny gives us, and Piaget said it, I think, best, he said, there are children all around us. They're developing. If we want to understand development, we should understand children. Actually, Piaget was not that interested in children, but that's another story. For my first probably 15 years as a professional, This is an approach that I took very seriously because my early work relied very heavily on the theories of Piaget. Reverse engineering is something all evolutionary scientists do. And basically this is trying to understand the evolution of a system by identifying what it was designed to do. Okay? And most famously in evolutionary psychology is David Buss's work on waist-hip ratio. Anybody have a hard time identifying the boys and the girls in this picture? No, and it turns out we're very good at detecting the opposite sex from hundreds and hundreds of meters away. Our perceptual system is very sensitive to that. So we can ask the question, why? Well, the answer is obvious, right? You want to be able to identify mates and potential mates. So that's reverse engineering. Archaeologists, though, are a little suspicious of reverse engineering. I'll just give you one example from human evolution. It's not really archaeological, it's bipedalism. Before 1960, anthropologists were absolutely certain about why bipedalism evolved. It evolved to free the hands for tool use. That's reverse engineering. I mean, that's what it does for us. That's why we have it. Wrong. Okay. Turns out chimpanzees use tools. Lots of animals use tools, and they're not bipedal. And then the other thing, the real clincher, is bipedalism evolved about 4 million years before any evidence for extensive tool use. So the problem with reverse engineering is we all do it, but we also have to be able to check it from some other lines of evidence. And brings us to what I do, which is cognitive archaeology. And all of these objects that I show you up are over 25,000 years old. Actually, they're all probably over 30,000 years old. And if we just look at this one for a moment, it's pretty fascinating, right? Here we have an object that has the head of a lion and the body of a person. Okay? It's probably 36,000 years old. Does that have any cognitive implications? What do you think? Yeah, it's sort of fraught with them. The problem, though, is we tend to approach it from a common sense level, and if we want to do science, we have to do a little bit more than that. So first we have to ask the question is whether products of action actually indicate anything reliable about cognition. And it turns out that psychologists use products of action all of the time. On the right, what you see is a test for brain damage, something called lateral neglect. They ask people to copy drawings, and you see this person copies the drawing, but everything on the left side of the drawing is missing. Okay? That's because they suffer from cognitive neglect, which is a kind of brain damage. And on the left, we have children's drawing. I do have to say at least one funny anecdote. I was once really into children's drawing about 20 years ago, because I thought I could put together an interesting argument that spatial cognition evolved long before symbolic cognition. In children, they evolve hand in hand. And so I was looking at children's drawing, and I wrote this great paper and sent it off, and I discovered very quickly that experts in children's drawing do not play nicely. I have never had such savage reviews. Even from other archaeologists. I have no idea what I said, so I gave up on that. But to really put together an argument in cognitive archaeology, you have to really put together a series of linked inferences. And this comes from a paper I wrote several years ago for PNAS, in which I analyzed a cognitive argument made by Lynn Wadley. And basically, there are a series of inferences, B, D, and F, or inferences. In the first case, what archaeologists find are an artifact or a feature. In this case, it's a little stone tool known as a segment. If you look closely, you can see a little bit of red coloring on it. This is called red ochre. It's an ochre color. And so what Lynn Wadley did, based on ethnographic analogy and also experimental archaeology, was able to demonstrate that this was a component of a projectile system in which the artifacts were mounted like this. Okay. And then, based on more experimental archaeology, again the inference D, she was able to reconstruct the knowledge system that was necessary to produce this. Then, the next step, by applying this information with a model of cognition that she borrowed from Phil Barnard, was able to argue that this is evidence of abstract reasoning. Now, I should tell you right off the bat, I don't believe her. But the important thing is the structure of the argument itself and how it works. And you might say, quite reasonably, that if you have a series of linked inferences, that as we move down the chain of inferences, the probability of success declines dramatically. So if you say, okay, we have a 90% chance here and a 90% chance here and a 90% chance here, what's the chance of the whole thing being? And then you sort of get really discouraged and go into psychology instead. But the advantage we have in terms of cognitive archaeology is we're looking at stuff that actually was made in the past. And this is really our only direct evidence of prehistoric activity. And even though the reasoning itself might be a bit attenuated, it's the only way really to do that. Now, of course, there are caveats galore, which I'm not going to go into in detail. I think about them all of the time, as you might imagine. One of the important ones is the link between action and cognition. Turns out psychologists don't like to test for the things that archaeologists find. They find it's too dirty. You can't bring it into the lab, it smells. And so they like to do other things. And so this is something that we have to try to do on our own, and that's a bit tough. One of the things I'd like to do with the Center of Cognitive Archaeology is actually begin an active experimental program in which we try to solve some of these issues. Other issues, of course, appropriate cognitive models. There are cognitive models galore, and some of them are friendly to doing cognitive archaeology, some of them are not. There are also archaeological challenges, the usual one, archaeological preservation. The farther we go back in time, the less there is to find. And so we end up seeing a very narrow slice of behavior. And that's troubling in many respects because we can ask the question, what don't we see? But that gets really dangerous if you start just relying on what you don't see as opposed to the things that you do see. Then we have a problem of what we call equifinality and parsimony. Often in archaeology, there are several ways to get to the tool that you find. And based on law of parsimony, you have to take the simplest one. And what this means is we sometimes underestimate the abilities of prehistoric people. How are we doing time-wise? Not too bad. All right, let's talk a little bit about patterns in evolution. We won't do this very much. This is everybody's sort of standard average view of evolution. And you've sort of the cartoon version, you know, Australopithecus evolves into Homo habilis, into erectus, into Neanderthals, into us. We can do it with brains. Everybody's happy with that. That's not how evolution works. Yeah. This is a much better summary of what we know about human evolution based on the fossil evidence. Each of these bars represents a fairly well-defined fossil taxon, and this is the temporal extent of it. So you can see here we know a whole lot about Australopithecus afarensis. But we have other things as well. We got this weird one down here, Ethiopicus. We don't know anything about it, hardly, except we've got one skull. And what I love are the question marks all over the place. These are the connections. And we don't find the connections. We have to infer the connections. And this makes for a lot of fun and a lot of argument and a lot of heavy drinking. But you can see that the vast majority of human evolution going back 5 million years consists of these sort of isolated bars of things with our attempts to put them together. If we ask the question, what are we really confident of? We go here to Homo sapiens. We're confident Homo sapiens evolved out of Heidelbergensis, and we're confident Homo Heidelbergensis evolved out of what they call Homo ergaster, which I would call Homo erectus. That's it. Before that, it's almost anyone's game in terms of who's related to whom. Another misconception about evolution is that it's gradual. That is, it's just been a nice gradual change into modern humans over the course of several million years, and that's not the case at all. We often use the term Mosaic evolution to describe how evolution occurs. Complexes of characteristics evolve for particular reasons in the past. And if we look at sort of the three major anatomical components for hominines, these are bipedalism, change in teeth, change in brain size. They actually evolved at different times in different contexts for different reasons. And so we describe that pattern as being a mosaic pattern. And the pieces might not fit directly together in any way. The relationship of brain size to bipedalism, there doesn't seem to be any, as far as we know. So let's take a look then a little bit at cognitive evolution. I've been doing this for 40 years now. And these are some of the things I've looked at in the course of my career. We'll talk about some of them. a little bit later, and we can sort of set them up in a time frame. It's a little bit like a mosaic. So the earliest thing I've ever talked about was what we call action level imitation. And recently, most recently, I've been working with Fred Coolidge to talk about working memory. Now, what I was hoping to get is the same reaction that John Belushi had when they put up Flounder's picture in Animal House. I didn't get that, but most of you know Fred Coolidge. Fred walked in my office famously when I was associate dean, and I think I was signing suspension letters, if I remember. And he said he had an idea. And I said, great, it's better than a suspension letter. Come in and talk to me. And he had this idea about the very last step in the evolution of human cognition, which was an evolution in working memory capacity. Many of you heard me talk about this. Fred is not here. Fred is on an airplane going to Italy, where he will be sitting in nice piazzas drinking wine. So let's forget this. Let's talk about spatial cognition, which in a way is the first thing that got me into this. A lot of geographers in here too, so that'll get the geographers all excited. This has sort of warped some things here. Spatial cognition really means our ability to organize ourselves in space, the way we move in space, the way we manipulate space. That's spatial cognition. And here are a number of famous examples. This fellow, if you're curious, is in an orienteering competition. Very popular in Europe, not so popular in the United States. I want to start with a few examples. Spatial cognition is actually very important for us, and we're actually very good at it. This is a famous example. Some of you recognize this. This is from the Shackleton Expedition to the South Pole. 100 years ago now. We're almost to the anniversary. And if you remember the story, the Endurance was crushed by the ice, and they went off to manage to make it to Elephant Island. This is an actual picture of their launching this boat because Shackleton and 5 of his crew traveled from Elephant Island to South Georgia Island right here, which is a distance of about 750 miles. Across this ocean, this is really what that ocean does. This is the most violent ocean on the planet. The story goes they could make 2 sun sightings in the entire trip. So in the course of, I think, 10 days, they sailed from this speck to this speck across the ocean. Really a remarkable feat. Now, they had some help. Okay? They had a clock, and they had a compass, and they had a sextant. You all know how to use a sextant? Imagine using a sextant on this. Okay. Really very impressive, and it attests to our ability to find ourselves in space and travel in space. But unless you're really impressed with that, this is even more impressive. This is Micronesian navigation. Think of the Pacific Ocean. You all have a good picture of it. Here's Saipan, Guam here. These are the Micronesian islands. Palau over here. Truk is right here. The island will be worrying a little bit about its Puluwat. It's right here. Micronesians regularly traveled in these canoes to small islands over the horizon, sometimes on direct journeys of over 100 miles. Now, the longest journey they would ever make was from Saipan down to the Micronesian islands. They didn't do this very often because, among other things, it was dangerous. But how'd they do it? This is one of the gadgets they use. It's actually a little bit deceptive. It's really just a mnemonic device. It's a device that each of these little nodes is an island, and it allows them to recite all of the information they've learned about how to get from point A to point B. But really, everything is learned orally, and everything is held in long-term memory. And they have a very interesting way of doing it. If nothing else, this is probably the most interesting thing I'm going to talk about today. Something called the Etax System. Some of you may be familiar with it. It's based partially on a sidereal map of basically the rising and setting of stars. So where Vega rises on the horizon, where Vega sets on the horizon. This is a sidereal compass. And Micronesia is close enough to the equator that it doesn't really change that much over the course of the year. So this is how they orient themselves in space. That is, they orient themselves with an astronomical system. But to navigate, you also need a system of tracking your progress. And this is the most interesting one. It's called the Etax System. And what they do is think of an imaginary island called the Etac Island. And they think of it as traveling across the horizon beneath these stars in the places where they set or they rise. And they use this as a way of dead reckoning. And is dead reckoning the amount of time they've been traveling. And doing this system, they can hit a small atoll, basically a palm tree high above the ocean, over 100 miles away. The most impressive thing is they occasionally do it at night after heavy drinking. That really impressed me. And they don't have clocks, they don't have compasses, they certainly didn't have a sextant, and yet they had a way to navigate these vast distances. It turns out that we use two cognitive systems in thinking about space, and especially in navigating. One is called route following, and the other is called survey knowledge. There's some other terms that we use for this. If you think about getting directions from MapQuest or Google Maps, this is what you get. After Park Street, you'll need to continue and take a ride on Sumner Street and continue on to Holland Street, past the Tate Modern. Clearly, we're not in Colorado Springs, right? Yeah, I wish I were going to the Tate Modern, but no. Okay, so this is a perfectly good way to get around. And if you think about it, if somebody calls you on the phone and asks you, how do I get to your house, this is what you do. Is you give them basically a route following. And it's based on landmarks and visual positions and turns. Okay? But the other kind of knowledge, survey knowledge, is rather different. This is a map, clearly it's a map from an orienteering course, and it's a bird's eye view of a route. And to use this, what you have to be able to do is conceive of a visual perspective that you don't actually have. That is, you can't fly up in the air and look down on the landscape, usually. So this is something you construct cognitively. So that's very interesting. We have a name for that, actually. It's called allocentric perception. And it gives us, it turns out, an avenue to talk about the evolution of these things. Because it turns out, based on the work of Erwin Silverman, who's an evolutionary psychologist, that there's a very high correlation between survey knowledge and mental rotation. Now, mental rotation, you may remember those exciting intelligence tests you have to take where they say, look at this block, find the one that is a rotated version of that block. I always like to give this test and see how many of you actually get the right one, but we won't do that. Because then people argue, which is just silly. I have no idea. Turns out this whole ability to visualize how the block will look from another perspective is based on the same thing that survey knowledge is based on. And this gives us an avenue into evolution, because one of the things archaeologists have is a record of stone tools going back over 2.5 million years. And this is what I've primarily been doing for the last 40 years or so. A little bit about stone knapping first. I get this guy because he's really not very buff, right? So he's saying, okay, if he can make it, I can make it. Anyway, stone knapping is basically a subtractive task. You take a hammer stone, you strike it on the edge of what's called a core, you break pieces off. Now, one of the few sort of insights I've had in my life was that stone knapping is primarily a spatial task. That is, it relies on your ability to organize space and to deliver actions in space. Nobody on my dissertation committee challenged it on me, so I thought I must know what I was talking about, right? And then 25 years later, Nick Toth, who's a fellow I've known for years at University of Indiana, who's a good stone napper, decided he wanted to know what the brain was doing in stone napping. And so he didn't inject himself, he had somebody inject him with the radioactive tracers. And then he napped away on a core, just basic stone napping, Rocky, just basic napping. And then jumped in the PET scan machine, and this is what we get. So if you look here, it looks down from the top, what you see is activation high on the backs of the head, which is the parietal lobes of the brain, and guess what the parietal lobes of the brain do? Primarily spatial cognition. So what they were able to confirm, so I'd been right for 25 years. And so I actually have a bet with Nick about some things. I'll talk about that. So this brings me to really the first serious archaeological bit here. The first set of stone tools, they're called Oldowan or Mode 1 tools, were manufactured between about 2.6 and 1.4 million years ago, a long time ago. And when I looked at these things in my dissertation research, they looked pretty simple. And from a spatial perspective, they are pretty simple. Basically, you just have to knock pieces off next to other pieces, produces sharp edges. There are no overall shapes to these objects. And I said, okay, that's interesting. Then I looked at the non-human primate literature, and it turned out that that kind of spatial cognition is typical of non-human primates, especially chimpanzees. So in 1989, Bill McGrew and I, who's a specialist in chimpanzee technology, published a paper in which we argued that basically all these early stone tools are well within the cognitive abilities of apes. A lot of my colleagues didn't take that very nicely. But then Kanzi's famous for a number of reasons. But Nick Toth, he just saw his brain a little while ago, in the 1990s went down to Yerkes Primate Institute and taught Kanzi how to nap. Not sleep, but to nap stone. And there's a lot of famous stories about Kanzi. So Nick demonstrated how to make stone flakes for about 2 weeks. He'd use the stone flakes to cut open a box and get a reward. And Kanzi thought that was pretty cool, so he paid a lot of attention. And then Nick handed the stuff over to Kanzi, and famously, anybody remember what Kanzi did? Any of the anthropology students? Kanzi jumped up on a file cabinet, took the core and hurled it down on the floor, where it shattered, and then jumped down and picked up a sharp piece and cut open the box and got the goodies. So this actually is really an interesting bit of information. Eventually, they had to take him outside in the woods where the ground was soft, and because that's what he wanted to do. And they eventually taught him how to nap like this. Now, it turns out that Nick and I have this bet that he says there's something Kanzi doesn't understand. And I said, no, Kanzi can do all of this, don't worry. But it turns out, really, there isn't something that Kanzi understands. But Nick can't tell me what it is. So since he can't tell me what it is, I don't think he wins the bet. But I can tell him what it is. Now, this, interestingly, is from a site called Lokaloli in northern Kenya. The site's about 2.3 million years old. And the interesting thing about this site is all the flakes were there, which meant you can take the flakes and glue them back together into the core. This is called refitting. And then you can examine the order in which the flakes were removed. As you can actually reconstruct the actions that were used. And it turns out that all of the cores were napped the same way. Basically, the stone napper would look for a usable platform, knock a few flakes off till it didn't work anymore, rotate the platform, knock a few more off, rotate the platform. All of the cores were done the same way. What this tells us is that they were not learning stone napping the way Kanzi did. That is, they were learning stone napping by actually copying the motor procedure for doing it. And this is something we call action level imitation. And this is one of the things that distinguishes us from chimpanzees. Chimpanzees cannot do action level imitation. They can reinvent the wheel. They're very good at that, but they're not very good at copying motor procedures. Which jumps up to 1.8 million years ago into the time period I'm most fond of. Something happens. A lot of things happen at 1.8 million years ago. But the most important thing for us is hominins started to make tools with shapes, in particular bilateral symmetry. So you can see it pretty clearly over here. There are basically two kinds of bifaces, pointy ones, which are called hand axes, and non-pointy ones, which are called cleavers. That's really not terribly important for us. And this is something chimpanzees cannot do. Not in any dream could they do this. Chimpanzees don't impose shapes on things. So the question then is, cognitively, what does that mean? If you know anything about visual processing, your brain processes visual information in two basic streams. First, the information passes from the eyes back to the occipital cortex, where the initial processing occurs. And then the dorsal stream processes visual information for space. We just saw something about that with stone napping. It's basically a spatial activity. The ventral stream, which runs along the bottom of the temporal lobes, especially a structure called the fusiform gyrus, is for shape recognition. That's where you recognize things like symmetries and faces. And that occurs in the ventral stream. So what we've got here is a coordination of the two visual streams. And that's interesting because that's something chimpanzees can't do, and that's a development in spatial cognition. A lot of other things happened 1.8 million years ago. This is only a partial list. This is when Homo erectus appears on the scene. First, we get geographic expansion out of Africa into Asia, into southern Europe. We get expansion of range size, that is the range at which hominins are moving. Cursorial running, which is distance running, is an adaptation that appears at the same time. Reduction in sexual dimorphism. The females got really big. The males, not much happened to the males, but the females got really a lot bigger, which has some interesting implications about social behavior that we won't go into now. Now it's beginning to look as if fire also makes an appearance that early too. This is a controversial topic, but I like early fire, so we'll say it happens then. Okay. And Fred's favorite, I put it even though he isn't here, I put it down here anyway, ground sleep. That is, instead of sleeping in trees, sleeping on the ground. So what's the problem with sleeping on the ground in Africa? Predators. Yeah, the things come along and eat you. So there are all sorts of things that have to happen in an adaptational sense if you're going to be sleeping on the ground. Then another thing is what we call curation of tools. They started carrying these things around. Prior to this time, they had a motor procedure for producing sharp flakes, but now they're starting to make tools. So we're going to jump up 1 million years to what we call late mode 2 bifaces or late hand axes. Both of these are sites that are probably only about 300,000 years old. And something has happened in terms of spatial cognition. In the last year or so, I've been working with an artist in Los Angeles who wants to put together an exhibition of hand axes as works of art. So we've been traveling around the world looking for cool hand axes, which is a lot of fun, by the way. Some of these are to give you examples of some of the really beautiful hand axes that we find. This one is from Mauritania, and a tradition developed in the Sahara Desert of producing huge hand axes. This thing weighs over 10 pounds. I mean, it's not the kind of thing you're going to pick up and shave with. And it's a little unclear exactly what they were doing with them because there's not much evidence of them actually having been used. This is a beautiful hand axe from England. This one actually is kind of important. It's a little hard to see what's going on. This is edge on. And you see the edge makes this nice twist. This is actually obsidian, so that's heavily hydrated obsidian. And it looks as if the stonemaker just, after finishing the axe, just twisted it like this. They're really beautiful artifacts. And these are my biggest puzzle of date. These shouldn't exist. They're from the Central Sahara. They're about the same age as this. They're about 500,000 years old. And they really do look as if they're figurative. That is, they've been made to represent an animal of some sort. And that's not supposed to be going on 500,000 years ago. Anyway, some other things we can see. Some of these are technically brilliant artifacts. So Rocky would be, no, he's going to leave so I can say some cool things. Our stone napper is leaving, so I don't have to make it up anymore. Okay. This is from a site of Boxgrove, famous for a lot of reasons. And after finishing the hand axe, what the stone napper did was hit it right on the tip and strip off a flake right here. What's surprising about that is after doing all that work, you put a blow on the hand axe, which has a very good chance of breaking the thing, that is shattering it. Same thing happens over here. You can see a little channel here. This is a beautiful hand axe. And at the end, somebody just hit it right on the tip and stripped a little flake off. It's like saying, I'm good, but watch this, I'm even better. So a lot of things start happening about 500,000 years ago. But what we're interested in terms of spatial cognition really is this first one primarily. If we back up, let's back up and look at this one. If you take this artifact and get a saw and cut it through at any angle, what you'll have is a cross-section that's perfectly symmetrical. Yet in making this, the stone napper can't see any of these cross-sections. So what's that suggest? Well, it's allocentric perception is what it is. That is your ability to conceive of three-dimensional solids that you can't see or can't sight is allometric perception. So that's the most important conclusion. Also, we see a lot of violations of symmetry. Clearly, they're playing with the whole basic idea. A lot of technical brilliance, some gigantism, some figuration. Fossil-wise, this is Homo Heidelbergensis. Homo Heidelbergensis had a brain that's in the modern range in terms of size. So what? I always like to ask, so what? What it tells us is allocentric perception is in use prior to 500,000 years ago. And assuming that allocentric perception is one of the keys to modern spatial cognition and modern navigation, what this tells us is that it evolved a long time ago, as it didn't evolve recently, prior to the appearance of Homo sapiens, prior to the appearance of modern culture. prior to the appearance of modern hunting and gathering. That is, what these folks were doing was rather different, and yet it's selected for a particular set of cognitive abilities. Interestingly, for those mathematically inclined, what we're learning now about the neurology of number concept, for example, is that it's built out of neural resources that evolved for spatial cognition. So it turns out that spatial cognition evolutionarily was very important for later developments that we generally talk about in terms of mathematics. So I have not a clue as to why I included this slide. Okay. We can sort of present a picture of a mosaic of cognitive evolution for the last 2 million years. It doesn't work very well chronologically, so don't worry about the dates. But spatial cognition evolves pretty early. Symbolism, we've talked a lot about symbolism, at least in the research that I've done, probably 500,000 years ago. Something called expertise, which is kind of technical cognition that I've looked at, probably about the same time. Executive control, which is working memory, really, is really the last piece in this puzzle of cognitive evolution. Now, there are other pieces, we just don't know very much about them, but I think it paints a very interesting picture of the human cognitive past. Thank you. So, questions?
Does spatial cognition develop earlier because it's part of survival?
I think so. Yeah, the best guess is that it's actually probably tied to spatial navigation. That is moving across the landscape. Because one of the things, we see two things really. One is the expansion of spatial range. So that the ranges of these early hominins were 10 times, 20 times as large as the ranges of chimpanzees. And you have to move about in the landscape. So one hypothesis, I think it's a pretty strong hypothesis, that was the major evolutionary payoff. The artifact stuff is just a side effect of that. That would be how we explain that.
Yeah. If I could follow up, when symbolism, when that ability starts to develop, is there a survival aspect of that? What's the advantage that?
The reason I'm hesitating is the single most contentious topic in human evolution is the evolution of symbolism. But yes, the usual argument is a social argument, that there are reasons for social marking and that symbolism evolved initially for social marking and then later gets borrowed into domains of communication and so forth. That's one of 20 extremely contentious hypotheses. The nice thing about symbolism is we don't know very much about it, so we can say whatever we want. Right? So, other questions? Lee?
Do other animals have spatial cognition?
Oh, sure. Not the way we do. Primate spatial cognition is because of binocular vision. Human spatial cognition has some other components, like allocentric perception, which non-human primates don't have. There are some animals out there who are wonderful navigators. Most of them cue into the magnetic field and navigate using that. Most people don't. I mean, back in the 90s, there were lots of experiments done in Scotland where they put undergraduates on a bus, and the bus was all blacked out, and they'd drive them around and ask them where they were. And all they could say is, we're not near a pub. So they weren't getting any kinds of reliable indications that we cue into the magnetic field of the Earth. But that's one way to do it, and a lot of birds are just spectacular navigators. A lot of fish are spectacular navigators. So the ability to navigate itself is not all that impressive, but the way we do it is interesting, and it seems among primates to be unique to us. Tom?
When did the concept of a god or a supreme being or something outside...
You really want to get me in trouble, don't you?
It seems like symbolism would be the time that...
It was on a Thursday, 44,000 years ago. Okay. Seriously, that's a tough one. Clearly, I think if we go back to the Hohenstein-Stadl figurine, I think the most parsimonious way to understand that is that it's some kind of icon in a religious system of some kind. That gets us back to about 36,000 years. Before that, is hard to say, because what we find evidence for body painting probably going back 200,000, maybe 300,000 years. At least we think that's what they were painting. Since we don't find what they were painting, we figure it was their bodies. But we don't know what that's for. So the association of a particular artifact with a particular abstract concept is really tough for us to do. And the oldest we've really got with any reliability would be Hohenstein-Stahl. So,
you think it would come from the time when humans started asking the question, why is this happening? Why is something occurring that they can't explain scientifically?
you would think so, but I'm guessing that's pretty late. That's sort of a metacognitive deal when you start reflecting on your own thoughts, and it's like sort of a metacognitive deal if you think about it enough. And that might require, Fred would say, that might require a modern working memory capacity, which is sort of the last thing to evolve. So, Rex?
You take allocentric perception to be a necessary condition for the production of stone tools.
Not for stone tools, for certain kinds of stone tools.
Certain kinds of stone tools.
Yeah.
Allocentric perception is a development out of spatial cognition.
Yes.
And what is it that allocentric adds to spatial cognition, the spatial cognition of other minds?
It adds alternative perspectives. So it allows you to, for example, imagine what a landmark will look like when you're coming back. You've seen it going out, but when you're coming back, how do you recognize it? Because it's coming from a completely different direction. So in a practical sense, navigationally, that's what it allows you to do. I don't think it's critical for stone tools, but then it gets invested in stone tools for other reasons.
That's what I hoped you would answer. It strikes me that what you're suggesting is that allocentric perception, unlike spatial cognition, adds some ability, cognitive ability, to construct mental models or mental images.
Yes.
If you apply the utility of mental images to the case of stone tools, are you not suggesting that the knapper holds in his mind or her mind the image of the tool that he or she wants to produce against the knap tool as it's so far produced?
Yes.
If that's the case, then isn't there a kind of executive control fairly deep back in time?
Yes. One thing about working memory, since we didn't talk about working memory, I didn't get to say, chimpanzees have working memory. So it's a matter of working memory capacity. And the question about executive control is a really interesting one. Remember I said a lot of things seem to happen 500,000 years ago? There are a lot of things that really are interesting 500,000 years ago that we haven't been able to make much sense out of. And so for this idea of mental models, and as a way to sort of operate in the landscape and even socially, is a pretty provocative one. And in some ways, I like to argue that's where we get the seeds for modern cognition, is back that far.
One of the things that's happening right now in philosophy of neuroscience and philosophy of mind is this dynamic embodied embedded view. And it's hostile to the notion of mental representation.
I know it is, yeah.
And yet, the view that you're advocating requires mental representations of some kind.
Yes.
And so a challenge for a view like yours against the dynamic embodied embedded view is to find a home, a neural home, for mental representations of some kind.
Right.
And there are models, hierarchical dynamic feed-forward models of cognition and perception that explain what happens when we anticipate future actions. We create efferent copies that are neurally grounded, and we can calibrate those efferent copies against what we expect from the environment. And we can then find a home for some kind of representations, even within a dynamic embodied.
Right. I mean, I'm attracted to the embodied cognition for a lot of reasons, but the extreme versions of it, I think, throw the baby out with the bathwater. And I don't think we can abandon representations entirely. Or I'd be out of business, and since I'm semi-retiring, maybe it's appropriate to do that. But that's one of the things, talking to Lambros Malforis, is because he's very much committed to the to the embodied extended model and doesn't give any, well, he doesn't say no credence, but he doesn't give much credence to representation. So. But he's a lot younger and a lot better looking than I am. Linda.
I'm not sure how to really phrase this as a question, but it has to do with local knowledge versus external, coming from somewhere outside a locality. When I went to Ireland, we were going to a bed and breakfast in this place called Youghal. And so we called the woman who owned the bed and breakfast for directions. And as a local who had lived there all her life, she said, "Oh, it's so easy. You just go down and there's the stop sign and the roads, make a V." Well, there were like 10 of those. So about like 2.5 hours later, we call her again now. And we finally got her. And then on the way home, so we go, she sends us to a late night pub so we could get some food. And then the people at the pub tell us how to get back to her place. Oh, it's so easy. 3 hours later.
Exactly, yeah.
So, I mean, is there anything about, the difference between local perception of space, and outsider's perception?
Sure, actually, Tim Ingold has talked about some of these things. He's a cultural anthropologist at Aberdeen. And what he talks about are vistas. That it's not so much route following as you have the visual vistas, and when you arrive at the appropriate vista, you make the appropriate action. So the local knowledge consists of all these vistas, and which seem perfectly easy to them. All the other roads are not part of any vistas that she has, so she doesn't report them. But you don't have these things, so you're just trying to route follow, and you're scratching your head about what's going on. So that's what Tim argues, and I think that's probably very much what happens in terms of local knowledge, because most of what we do seems to be more in sort of the route following thing. It's when we're pressed that we do these other kinds of navigational abilities. Of course, some of you may have argued with people about directions, following directions. And my daughters, and many of you have met my daughters, grew up in Colorado Springs. But I discovered once, they're in high school, and we're in one part of town, and they have to drop me off, and they have to drive home. And they said, "We don't know how to get home." What do you mean you don't know how to get home? We don't know where we are. We don't know how to get home. I mean, they'd grown up in Colorado Springs all of their lives, so I mock them about that regularly, So it's because, among other things, they spent their lives reading books while they were in cars, so they really didn't pay much attention. But they didn't have really a bird's eye view of Colorado Springs in their head. They had a series of vistas, a series of routes that they took. That's what they're familiar with. They didn't have a way to build a novel route home, and that's what these external frameworks allow you to do.
I remember talking to you in your office once years ago, and you mentioned in passing sort of a study, not about necessarily this having any kind of deep cognitive root, but that at least socialization perhaps, that looking at how women give directions versus how men give directions, and at least, and I don't know if that was just in the United States or if it was cross-culturally, but the sort of landmark route-driven versus the directional. Yeah,
there is a tendency, and I'll get into a lot of trouble for this, there is a tendency for at least women in the United States to use route following almost exclusively, and men are more likely to use a sort of survey knowledge. That is, well, you want to turn west on such and such a road, and say, what do you mean, what direction is west? But men actually, the difference is not all that great, and it's probably a bit of matter of enculturation. So.
It brings me to the Ireland story, because when I was in, when I was in Edinburgh, in Scotland, and part of it is an Enlightenment Grid city,
yes.
And then
the new town
is like Boston.
Yeah.
It's a medieval plan,
right.
Rotaries, 6-way intersections, and roads change names.
Mm-hmm. Sounds like Colorado Springs.
But it's not by blocks. It's
right.
not direction. And so the way people give directions there, men or women, it depends on what part of town you're in. Are you in the post-Enlightenment, kind of
right.
part of town, or are you in the medieval part of town? Because they'll say, well, the road name changes. I found it just impossible to either give or receive directions in the bed and breakfast that was in the medieval part of town, because it's like this. Which of the 5? There's like 3 right turns off of the rotary, and then the road changes the name, and then go around two curves, but how do you
Right.
define a curve?
Exactly. That's why they built pubs, so you
I don't
have
know how you
landmarks.
get directions.
And if you can't find where you're going, you still
I mean,
have a
it
pub.
has to be vista
So-
driven. In
Yeah,
a way,
it
directions
is,
in that part
yeah.
of town have to be clearly
Right.
vista.
so. Cool. Well, thank you very much. I think there's still some goodies over in 309, right?
Thank you, Dr. Wynn.